Junichi Tomida, and Junichi is going to give the talk.
Thank you for introduction. So I will explain my new result on quadratic functional encryption. So let's start with briefly recording functional encryption. So in functional encryption, there are 4 algorithms, and setup algorithm generates a public key and master secret key. And encryption algorithm takes a public key and message and generates a ciphertext. And in this talk, we assume that the message consists of a public part and a private part, and the ciphertext only hides a public part and private part. And the owner of the master secret key can generate a secret key that is associated to some function f. And the salient feature of the functional encryption is in decryption, the ciphertext for x and the secret key of f reveals only f of x and nothing else. And in this work, I will consider the notion of unbounded, which says that message size to be encrypted is not bounded by the public key. And in this work, we consider simulation-based security. And it basically says that actual ciphertext and secret keys can be simulated by only using the information that the adversary is supposed to run. So more precisely, we consider the 2 worlds. And in the real world, first the adversary obtains that ciphertext for challenge message, which is generated honestly. And then adversary can obtain the many secret keys as it desires. And in the simulated world, the challenge ciphertext is generated only using a public part of the challenge message. And then the simulated secret keys are generated using the function f and f of x. And the FE scheme is said to be secure if efficient adversaries cannot distinguish these 2 worlds. And next, I will introduce a motivation of unbounded functional encryption. And the problem of the most FE schemes is that the message length is fixed by the public key in the setup phase. But let us consider the system where we will encrypt the various sizes of data and assume that the fixed message length is as shown like this. Then we can encrypt the message that is shorter than the fixed message length, but by padding dummy data. But we cannot encrypt the message that is longer than the fixed message length. So how about setting the fixed message length sufficiently large? Then we can encrypt all messages by padding the dummy data. And are we happy? Of course not, because the ciphertext size is proportional to the message size, so such a way of encryption is very wasteful and inefficient. So in contrast, unbounded FE, in unbounded FE schemes, there is no need to pad the dummy data in encryption because unbounded FE is inherently supports the variable length. And also, there are no bound on the message size, so we do not care about the maximum data length in the setup phase. So unbounded FE is suitable for the system where we will encrypt various sizes of data. So let us review the previous works for unbounded FEs. The early works on unbounded FE focuses on the function class of Turing machine. So functional key is associated with Turing machine, and decryption reveals the computation result of Turing machine on the input message X. And disadvantage of these works is they rely on the obfuscation. And the first work that does not rely on obfuscation is for unbounded FEs of the class of inner product. So function key is associated with coefficients of linear function, and decryption reveals a linear function over the message. And recently, a new class of functional encryption for the class attribute-weighted sums is proposed from the MDDT assumption. And this is also computes the linear function over the private input, but the coefficients is computed from arithmetic branching program, which is associated with functional key and the public part of message UI. But this is, as far as I know, this is all unbounded FE schemes, but the all unbounded FE schemes that does not rely on obfuscation is all linear in the private input xi. So the natural question is, can we construct an unbounded FE scheme for quadratic functions or higher degree functions without obfuscation? And we give an affirmative answer to this question in this work. So our first result is the construction of unbounded quadratic functional encryption. And in this scheme, functional keys are associated with coefficients for quadratic functions, and the decryption reveals the quadratic function over the message. And our scheme is based on pairing groups and secure under the MDDH assumption and random oracle model. And our second result is extension to partially hiding functional encryption. And in this scheme, functional key is associated with a set of arithmetic branching programs, and the coefficient of quadratic function is determined by these arithmetic branching programs and the public part of the message. And our second result is basically obtained by applying a technique developed by we, which is presented in TCC 2020. So I will focus on the first result in the rest of the talk. So let's take a more closer look on the functionality of unbounded quadratic functions. The message of this functionality consists of index set S and ZP element xi, which is indexed by the index set. And the function consists of the target index set T, which specifies which indices will be used to decryption and compute the quadratic function, and coefficients Cij, which specifies what kind of quadratic function is computed. And the output of the functionality is if index set S contains all target index T, then quadratic function is computed. But if it is not the case, then nothing is revealed. So this functionality can be seen a kind of attributes-based functional encryption, which is introduced by Abdallah et al. And because we can see that S as an attribute set and T is a policy, and the relation of S and T decides the decryption condition. So I will next how to construct our quadratic functional encryption scheme. And actually, our starting point of our scheme is quadratic functional encryption scheme proposed by Lin in 2017. and which is a standard quadratic functional encryption scheme. So the message length is fixed at the set of phase. But in this talk, we will start from a quadratic FE proposed by Liefeld et al. At 2019, because this is the simplest quadratic FE scheme, and it's easy to describe. And also, it is sufficient for explaining the ideas of our construction. So in their scheme, if we set the message length n, then first we choose two vectors u and v, the length of which are n, and the public key is the group vector u and v, and this bracket notation denotes the element-wise exponentiation to the G1 group and G2 group of pairings. And encryption of X is done as shown like this, but the structure of these ciphertexts is not important here. So the important thing is that we can publicly compute the quadratic function value for coefficient vector C plus masking term from C1 and C2 and the coefficient vector C. And other than that, C1 and C2 statistically hides the information of vector X. So if we generate a secret key like this, so we set the secret key as a blue term, then pairing of C3 and secret key reveals the masking term. So by subtracting this masking term from the above term, then we can recover the quadratic function of with respect to vector C. Then how to make this scheme unbounded? So naive idea is generating a vector u and the public key vector u and v by a hash function modeled as a random oracle. But this idea does not work because if we generate vector u by a hash function, then we cannot compute a secret key efficiently because in the secret key, a vector u is in the group 2, so G2 groups. So we cannot generate this term. And actually, this problem is common in existing quadratic FE schemes. So to circumvent this problem, we modify the quadratic FE schemes so that it is hash function friendly. And new quadratic FE scheme can be written as follows. So now we remove the vector u from public key and master secret key because this term is problematic if we generate it from a hash function. And the structure of ciphertext is also modified a little bit, but again, the actual structure is not important here. The important thing is, again, we can compute quadratic function value plus masking term from C1 and C2 and coefficient vector C. And C1 and C2 statistically hides vector X. And the masking term can be written as at the left-hand side, right-hand side. So by setting secret key as blue term, then pairing of C3 and secret key reveals the masking term. And subtracting this masking term, we can obtain the quadratic function for coefficient vector C. And in this construction, we can use a hash function to generate vector v, because even if we generate vector v by a hash function, the secret key can be generated efficiently. But the problem here is that anyone can compute the secret key because now secret key does not contain any secret information. And as I mentioned previously, we want to have some access control property by indices set S and T, but this construction does not serve such functionality. So to solve these problems, we introduce additional layer, and first encrypt the vector S by the additional layer. And to encrypt, so by encrypting vector S, now the adversary cannot compute the masking term by itself by generating the secret key by itself. And we also encode the blue term by additional layer so that to compute the covered blue term needs a master secret key, and decryption of this red covered term and blue covered term reveals the masking term. Then we can solve the first problem. And to solve the second problem, we associate the blue term to the indices set T and the red covered term with indices set S. And we also assume that decryption is possible if and only if S and T satisfies the condition. Then we can solve the second problem. So what is the additional layer? So this functionality is exactly corresponds to the unbounded inner product functional encryption. So our final choice scheme is like that. So the setup algorithm generates the public key and master secret key of unbounded IPFE scheme, and now vector V is generated by a hash function. And encryption is the same as the previous scheme, but the C3 is now generated using the unbounded IPFE and by encrypting vector S. And the key generation algorithm is also the same as the previous scheme, but now secret keys are a secret key for unbounded IPFE scheme with respect to the blue term. Then in decryption, we can reveal the masking term if and only if S and T satisfies the condition. And this means that the quadratic function value is also revealed if the condition is satisfied. So in conclusion, in this work, we constructed the first unbounded quadratic FE scheme, and we also extended to the partially hiding FE setting. And our scheme is semi-adaptively simulation secure under the MDDH assumption and the random oracle model. And I also mentioned some open problems. And the most interesting open problem is that since our scheme is relying on random oracle, so how to remove the random oracle is a very interesting open question. And also, our scheme satisfies only semi-adaptive security. So achieving adaptive securities in the standard model is also interesting open problem. And even in the for standard quadratic FE, adaptive security is still elusive. Thank you very much.
So we have time for one quick question. Any question? Okay. So I have one quick question. Okay, you mentioned the open problem of removing random oracles. Is this something inherent in all unbounded FE constructions, or there are constructions that don't need this assumption? For example, for inner products.
So Could you say?
So do there exist unbounded functional encryption schemes without random oracles?
Yes, yes. So unbounded, unbounded IPFE scheme and the FE scheme for arithmetic branching program does not use random oracles. So in our scheme, we maybe use random oracle for the first time for constructing unbounded IPFE, unbounded FE.
Okay, thanks. Okay, let's thank Junichi again.
Thank you.
So the last talk of this session is multi-key and multi-input predicate encryption from learning with errors by Danilo Francati, Daniele Friolo, Giulio Malavolta, and Daniele Venturi. And Danilo is going to give the talk. Please start.
Thank you for the introduction. So I'm going to talk about predicate encryption in the multi-key and multi-input setting. But let's have a first overview. So we all know functional encryption and predicate encryption. So in functional encryption, there is a sender can encrypt a message, and later you can decrypt a function of the message. And in predicate encryption now, you can encrypt a message together with an input for the predicate, and you can later decrypt a message if the predicate is satisfied. So this primitive belongs to the single input setting simply because there is a single sender that can choose the input of the function or the message. But for the functional encryption case, we have the multi-input version. So now we have multiple senders, and we can encrypt multiple messages, and you can later decrypt a function of the messages. What we do in this work, we extend the notion of predicate encryption to the multi-input setting. And while we do that, we also define an intermediate notion that is called multi-key, that is essentially a single input predicate encryption, but where the key is split among multiple keys. I don't have much time, so I'm going to focus only on multi-input, and I want to stress that there is a recent work at Eurocrypt 22 by Agravat et al. That studied the same notion, but we have incomparable results in terms of construction, predicates, number of inputs, and assumptions. So predicate encryption, very high level. There is an authority that generates the master public key for the sender, and you then use the master secret key to generate the decryption key for the receiver. Then later you can use the master public key to encrypt a message with an input text, and you send the ciphertext to the receiver. And then the receiver is going to decrypt the message if the predicate with the input text is satisfied. So the security notion we are interested in this presentation, it's CPA one-sided security that at a very high level says that you don't reveal any information about the encrypted message and the encrypted input under the condition that the adversary do not decrypt the challenge ciphertext. So now let's see how does it work the multi-input case. So this is the two-input case. We have an authority that generates two encryption keys, and you send the two keys to the senders, to the corresponding senders. And then you can, as usual, you can generate the decryption key for the predicate, and you give it to the receiver. But now the functionality is that every sender can choose its own message and its own input, and then you can send the ciphertext to the receiver. And on decryption, the functionality is the following. So you decrypt both ciphertexts, and you obtain the same messages, the encrypted messages, if the predicate is satisfied. And the predicate now is going to be a two-input predicate evaluated over the input of the first sender and the input of the second sender. So the power of the primitive comes from the fact that you can interleave ciphertext, and also this is why the primitive is hard to build. So for example, when you take C1 and C2, you evaluate the predicate on some inputs, but if you change the second ciphertext, you're going to change the input of the second input of the predicate. In the paper, we extend the notion of CPA one-sided to the multi-input setting, and the one that you see here is the secret key case. That means that the adversary doesn't see the encryption keys of the senders, but you only have encryption oracles to the corresponding encryption algorithm, oracle queries to the oracle access to the encryption algorithms. And the security, it's at very high level the same of the single input predicate encryption with that says that you don't reveal anything about the encrypted messages and encrypted inputs. But here the definition is a little bit trickier because we have multiples. The challenge ciphertext is composed by multiple ciphertexts. So we need to claim that the adversary do not decrypt any part of the challenge ciphertext. And this means that independently of what you can interleave, then any part of the challenge ciphertext it's not decrypted, and the ciphertext you can combine are the one that you obtain from the encryption oracles or the one that you obtain during the challenge phase. So we have a construction for this setting. We achieve adaptively secure CPA one-sided multi-input predicate encryption in the secret key setting. The number of inputs can be any polynomial in the security parameter, and the assumption is sub-exponential WE. And the class of predicates that we support is the one that you see here. So it's essentially a conjunction of arbitrary predicates, where each predicate takes in input one input of the corresponding sender. So for example, P1 takes in input the encrypted input from the first, encrypted by the first sender. We build it using these ingredients. So we use symmetric key encryption, adaptively CPA one-sided single input predicate encryption, and lockable obfuscation. And the reason why we need sub-exponential WE is because from AWE to get adaptive security, we need complexity leveraging. So I'm not going to talk about, the construction is secure in the case of a single decryption key. So that adversary only sees a single decryption key for a predicate. May seem like a very restricted case, but technically speaking, if you support very large class of predicates, this notion implies strong primitives like witness encryption and null IO. I'm not going to talk about this construction, and I'm going to move on in a much more challenging case of security. So this is the corruption setting now. And there is an additional oracle that you can submit an index, and you obtain the encryption key of the corresponding encryptor, or the corresponding sender. The definition is as before, but the difference is that now, since you can encrypt you can corrupt one of the senders, you can get the corresponding encryption key, and you can try any possible input for the corresponding slot. So we need to claim that the predicate is not satisfied, even if you try any possible combination for the corrupted slots. We have another construction for this case. So we obtain adaptively CPA one-sided secure multi-input predicate encryption, but now the number of inputs must be constant, and we tolerate up to n-1 corruptions. We still use sub-exponential WE. The class of predicate is the usual one with a difference, and the difference is that each predicate of the conjunction presents a wildcard. So there is an input that satisfies the predicate, depending on which one you choose. And I want to stress that the wildcard is needed both for functionality and security. And these are the ingredients that are essentially like the one of the previous construction, but we replace symmetric key encryption with public key encryption, but the construction is completely different. And technically, we don't even need predicate encryption in this case. It's sufficient to use an attribute-based encryption scheme. And the construction is still secure in the single key case. So I'm going to talk about the construction. So let me introduce first lockable obfuscation. You can obfuscate a circuit C using a lock Y and a message. You obtain an obfuscation that has a slightly different functionality, and the functionality is the following. So on input text, the obfuscation is going to output the message if C on input text outputs the lock. And the security says that, very informally, that when you don't know the lock and the lock is random, then you can simulate the circuit. How we can build the true input predicate encryption using these tools? Well, let's talk about the first sender. You have an encryption key that is composed by the master public key of a single input predicate encryption, a public key 1, public key 2 of the public key encryption scheme, and the secret key number 1 corresponding to PK1. What you do, you sample 2 locks, and we're going to call outer lock and inner lock. We are going to encrypt both of them using the predicate encryption scheme, and since it's a single input predicate encryption scheme, we need to choose the input at the moment of the encryption, but we assume that the input is composed by two parts. So the first part, we're going to put the real input, so x1. In the second part, we're going to put the wildcard. Then I'm going to encrypt this ciphertext C twice using the public key encryption scheme, using PK1 and PK2. We obtain W1, and then we start producing some obfuscation. So the first is an obfuscation of an inner circuit with hard-coded W1 and SK1. We're going to use the inner lock, and the message is going to be SK1. And we also obfuscate another circuit. You have the same hard-coded informations, but now we are going to use the outer lock, and the message is the message you want to encrypt, so M1. And this is the ciphertext. On the second sender, you essentially do the same with few differences. So now you have the secret key number 2, because you are the second sender. And then when you encrypt using the predicate encryption scheme, you're going to put the wildcard in the other slot, so in the first slot, and the real input in the second one. On decryption, you have a decryption key for a predicate that is simply the decryption key of the predicate encryption. And the predicate is this one, in the single input case. So you have an input composed by x1 and x2, and then it's a conjunction of two independent predicates. You can use this key to decrypt. How you decrypt? So we have a bunch of obfuscations. What you do, to get M1, you run the outer obfuscation with input the decryption key for the predicate and the obfuscation of the inner circuit, but of the other sender. So the obfuscation number 2. And to get M2, you do the symmetric case. So you run the outer circuit of the second sender, on input the decryption key for the predicate and the inner circuit of the first sender. You get both messages. And of course, decryption works depending on how you define these circuits. They're fairly complex, so I'm going to show you just a graphical representation of how to get M1, for example. So this is what you execute to get M1. And remember that attached to this obfuscation, you have these informations. And we need to know that we have SK1 hard-coded into the obfuscation. So what we can do, we can run the inner circuit, we input the decryption key for the predicate, and we pass the secret key number 1. These are the information attached to the obfuscation of the inner circuit. And note that we have SK2 as the message, and also are coded into the circuit. So now we have both keys. We can decrypt the 2 layers of public key encryption, and we can decrypt also the predicate encryption ciphertext. If you succeed, we know that the second predicate is satisfied, and we only know the second predicate because the second sender has put the wildcard in the first slot. But this is sufficient to return the correct lock, and this is going to release SK2 to the other circuit. Now the other circuit has both keys again. I can do the same computation. But now when you succeed, then you decrypt the predicate encryption ciphertext. You know that also P1 is satisfied. And you return the message. To get M2, you do essentially the same computation, but for the symmetric case. So we can generalize the technique for n greater than 2, but it has some technicalities to some challenges. So the high-level idea is that we're going to have multiple layers of public key encryption, one for each sender. So we're going to have n layers. And we're going to have n inner circuits. And during the decryption, we're going to start executing the inner circuit one into the other. And every time we pass a new secret key into the next one. So the last one you execute has all the secret keys, and you can decrypt every layer and then the predicate encryption ciphertext. The problem is that you need to check the conjunction is satisfied, you need to give the secret keys to an inner circuit. And since lockable obfuscation is not strong enough, we need to run the same inner circuit multiple times. So the execution is like an n-ary tree of 8n, and that's why we support the decryption time is n over n, and we support only constant inputs. And I'm not going to talk about the security, but I want just to say that we tolerate corruption because we have multiple layers of public key encryption. Until, if you have one honest standard, there is one layer you cannot decrypt. And the wildcard is fundamental, and it's not easy to remove, because if you have the same construction for the same class of predicates in the corruption setting, without the wildcard, then the construction implies witness encryption and null IO. So it's not trivial to remove. Some other considerations, we extend the results that we have from the CPA one-sided setting to the CPA two-sided, but this requires to use a two-sided predicate encryption scheme already. And we showed also that multi-key with CPA one-sided security implies matchmaking encryption with mismatch security. And we can see multi-input predicate encryption with corruption like some form of, weaker form of non-interactive MPC for the function that you see here. Yeah, that's it. Thank you.
So if you have a question, please come. You can come to the mic.
So I wanted to ask about the number of keys. So you said that if you support multiple keys, then it has implications to hard things like witness encryption. But that's only if you allow user corruption, right? So if I don't care about user corruption, then there's no fundamental barrier to supporting many keys, is there?
So the situation is that if you support corruption, we just need, assuming that we support arbitrary predicates. So, sorry, for the case of
I don't care about corruption.
Okay.
I don't want corruption. In that case, I think that, I mean, one should be, there's no barrier, right, to supporting many keys.
You mean decryption keys or encryption keys?
No, function keys, decryption keys.
No. I mean, I don't think there is a barrier, but our construction doesn't achieve that.
But there's no, that's what. So
Yeah,
there's no barrier. So
correct.
in your construction, what goes wrong? Like if I ask for 2 keys?
Yeah, because we use the single input predicate encryption as a black box. And to start the proof, we need to assume that there is one predicate of the conjunction that is never satisfied, independent from the interleaving of the ciphertext. And we are sure about this case only when you have one decryption key. Because otherwise, think about you have like a conjunction of 2 predicates. It may be that the first is not satisfied and the first one is, so the first is not satisfied and the second one it is, but also the other way around. So you may have another key in which now it's the symmetric case, and we cannot do the proof in this case. So we need that one is not satisfied always.
Okay, thanks.
Okay, so if there are no more questions, let's thank Danilo again.